The Pickle Battery. You push two metals into a pickle. One is zinc and one is copper. These two metals have different reduction potentials. Reduction potential is the tendency of a substance to gain electrons, positive reduction potential, or lose electrons, negative reduction potential. It is measured in volts. Copper has a higher reduction potential than zinc. So zinc, with a lower reduction potential, will give away electrons to copper. If these two metals are dry and have limited contact with each other, solid zinc will give electrons to the solid copper. This reaction is very slow and may take years or even decades to occur and only results in what we call corrosion. However, if these two metals are placed in an electrolyte solution with an electrical circuit between them, the situation changes. An electrolyte solution has positively and negatively charged substances called ions dissolved in it. An electrolyte allows for the free movement of ions, which permits electricity to be conducted. Salt water is an electrolyte containing sodium and chloride ions. The brine solution used to pickle cucumbers is made up of sodium chloride dissolved with vinegar in water. Pickle brine is also an electrolyte. Now place the zinc and copper electrodes into an electrolyte. Connect them in a circuit and electricity is produced. We'll explain how that electricity is made by looking at 1/2 of the electrochemical reaction first, then we'll look at the other half, and finally put the whole process together. Zinc, on the surface of what we now call the zinc electrode, will lose 2 electrons. Given an easy path through a conductive wire, the electrons flow to the copper electrode and you get electricity, the energy that results from the flow of electrons. If enough zinc atoms lose enough electrons, the resulting current may be large enough to power a small load. The loss of 2 negatively charged electrons turns a zinc atom into a charged zinc ion, Zn+2. The resulting zinc ion, Zn+2, dissolves into the electrolyte. As more zinc reacts this way, positively charged zinc ions repel and move away from each other, diffusing through the electrolyte. Now we'll shift our attention to the copper electrode, the other half of what happens in a pickle battery. Electrons from the zinc electrode have done their work and have been pulled through the circuit to the copper electrode. Remember, with a lower reduction potential, zinc will give away electrons to copper. On the surface of the copper electrode, 2 electrons interact with copper ions, Cu+2, that are present in the electrolyte. The copper ions gain 2 electrons to form copper metal, which is deposited on the surface of the copper electrode. There is actually much more to the reaction at the copper electrode than we will go into here. We've focused on copper ions gaining electrons in the pickle battery for a specific reason. It's a metal in common use in many commercial batteries. But in point of fact, the reduction of copper in a pickle battery lasts for only a very short time. The reason? There simply aren't many dissolved copper ions in the electrolyte solution, which is mostly salt and vinegar, inside a pickle. After the copper ions that are present are quickly reduced, other ions in the electrolyte are reduced in their turn, since we've learned what we need by describing the copper reduction reaction, and since the reactions with these other ions aren't as meaningful to this program, we'll leave their discussion here. The reaction at the copper electrode also helps zinc ions from the zinc reaction diffuse through the electrolyte. The reaction here decreases the number of positively charged ions, providing a region of negative charge to which positively charged zinc ions are attracted. This promotes the diffusion of zinc ions throughout the electrolyte, which serves to balance the charge in the electrolyte and encourages the overall reaction to continue. It's important to understand these two half reactions actually occur at the same time, And considering the enormous number of atoms and ions that are located even in the smallest space, it's accurate to say these reactions occur simultaneously millions of times each second. The half reactions in the pickle battery will end when one or the other of the reactants is used up. That's why a commercially made battery will carefully match the amounts of these reactants so that the capacity of the active material at one electrode matches the capacity of the active material at the other electrode. In other words, the active material losing electrons is sized to lose all of its electrons, and the active material gaining electrons is sized to gain all of the electrons lost with no room available to gain more. During this process, unwanted side reactions can also limit battery discharge by contaminating electrode surfaces or the electrolyte. It's also useful to understand that environmental conditions such as temperature will influence how a battery or electrochemical cell works. All of these factors apply to other batteries we'll consider shortly. We'll conclude this chapter of the video by recapping and adding some critical vocabulary. Batteries provide a flow of electrons. They do this through chemical reactions that involve the transfer of electrons from one chemical substance to another inside an electrochemical cell or battery. These electrochemical reactions are called oxidation-reduction reactions or redox reactions. Redox reactions always involve the movement of electrons. Set up as you see, zinc on the surface of the zinc electrode loses 2 electrons to the copper electrode. Loss of electrons is called oxidation, and this part of the electrochemical reaction is called the oxidation half reaction. The end of the battery or battery terminal from which electrons flow when in use is called the anode. The anode is oxidized, and this end of the battery, this terminal, is given a negative designation. Zinc ions left behind from this reaction diffuse throughout the electrolyte. At the copper electrode, copper ions dissolved in the electrolyte gain electrons that were lost by the zinc. The product is pure copper metal, which is deposited on the surface of the copper electrode. Gaining of electrons is called reduction, and this part of the electrochemical reaction is called the reduction half reaction. The end of the battery or battery terminal to which electrons flow when in use is called the cathode. The cathode is reduced, and this terminal is given a positive designation. This reaction also helps zinc ions from the zinc reaction diffuse throughout the electrolyte. To repeat, it's important to understand these two half reactions happen at the same time, involve the same number of electrons, and with an enormous number of atoms, ions, and electrons, even in a pickle battery. Finally, could you have predicted the voltage of your pickle battery before taking measurements? Yes and no. Copper and zinc have different reduction potentials. Copper's reduction potential is 0.34 volts. Zinc's reduction potential is negative 0.76 volts. From these values, we know a copper ion will take electrons away from zinc metal. The difference in their reduction potentials is 0.34 volts minus negative 0.76 volts, which equals 1.1 volts. Theoretically, a pickle could be a 1.1 volt battery. However, actual measurements fall short of that number. Pushing pieces of metal into a pickle with vinegar as the electrolyte makes for a pretty crude battery after all. But even with a well-engineered, well-made battery, factors besides reduction potentials matter. The nature of the materials in the battery and their purity, the type of electrolyte and its concentration, and always the environmental conditions around the battery. Though these and other factors matter, battery voltage determinations always begin with the reduction potential difference between anode and cathode materials.